Okay, it's Sunday morning. It's September 27th, and we're going to start by going over the homework assignments and maybe answering some questions as they arise. So I'm gonna go with assignment 2A. Now 2A is the material that we covered this past Monday, and it's covers probability. You remember we did some work with Venn diagrams. We talked about conditional probability. We looked at diagnostics tests, sensitivity, specificity, predictive value, and we use Bayes' theorem, which is a way for us to analyze a conditional probability to determine what a predictive value might be for a diagnostic test. So I'm going to go into that, and I think that covers a lot of that kind of stuff. So I'm going to open it up in my window. So this is basically what you would see when you do the assignment, or pretty close to what you would see when you do the assignment. So one of the first things we looked at was the Venn diagrams. Okay, and these are a way of describing populations and what the probability that one part of the population would satisfy one criteria or another criteria, or both at the same time, or either one or the other, or neither. In fact, as a matter of fact, or any one of those possibilities. So the way that this works is you had the opportunity to choose which of these descriptions are appropriate for the particular diagram that we're looking at. Okay, and instead of just going into those, we're going to take a look at this and we'll see what this says. Now, first, one of the things we deal with most often are the symbols that represent union. Here's union, it looks like an uppercase U, and intersection, looks like an inverted U right down here. Union means that either one of these conditions is satisfied or both. All of that is perfectly okay. So, for instance, A union B would mean that we find A acceptable, B acceptable, and anything that contains both A and B. So here we go. Here's A, here's B, and here's the region in the middle where it satisfies both A and both B. Okay, so that would be A intersection B. Oh, excuse me, A union B. Okay, so now intersection is a little bit different. Intersection, we are saying that it has to satisfy both A and B. Okay, so now if I take a look at that, well, let's see, what would satisfy both A and B? Well, this section in here satisfies both A and B, so it's A intersection B. Okay, so now what might we run into next? Well, next thing we might run into is the idea of this prime, which represents not that value. In other words, A with the intersection of not B, right? So that has to satisfy, since it's an intersection, it has to satisfy both of these things. Or we have over here, we have A intersection B again, and not A intersection B. Do we have one that's intersection? Nope. Okay. So I'm going to go through these with that in mind. Okay. So we know this is A intersection B. Now, here we got an interesting one right away. This one, A satisfies us, but B does not satisfy us. So this, we can't just say A, right? Because we want to exclude this region, which includes B, right? So we might say that this is the union between A and, intersection between A and not B, right? We don't want to include B. We want only that part that satisfies A. Okay, and this is A, and this is B intersection not A. I think I saw it down there somewhere, didn't I? This is A union B, and this is just plain old B, right? Do we have that there? Do we have an A? I think that's an extra. That's an extra consideration. A that none of these satisfy just A. Oh no, here everyone. There we go. Bingo. There it is. Okay. So I mean that's pretty straightforward, right? It's a little bit confusing sometimes because the notation might be new to you, the description might be new to you, but should be. I think you guys will figure it out. Okay. So next thing we looked at was probability. Was diagnostic tests. Excuse me. Okay. So let's take a look at question number 2. Calculate the prevalence of cooties for this population based on a random sample of the population. So we randomly sampled 1,200 people in this population. And we found that 150 of those people have cooties, and 1,050 of those people don't have cooties. So our prevalence, or our estimate of the prevalence, right? If this is, we could either assume this is the entire population for our purposes, or we could say that this is a very large sample and something that we think is really representative of the population. So our prevalence, I'm going to open up Excel because I like using Excel for something like this. And in fact, I may have given you guys a template for this. Let me see if I can't find it on Blackboard. Let's see. Okay. I think in homework 2 here, let me see. I don't want to open and answer one yet. Okay, here we go. I think this is a template that I made up that you guys can use if you want to. I'm going to change this now, just so that when you do it, you'll have the opportunity to do it yourself from scratch. I'm going to change the number of people who have cooties to 200. Okay, now that's going to change these numbers up here, right? So I might be changing this number to, oh, no, actually it adjusted automatically, I think. Yeah, it adjusted automatically. It kind of gave something away there, but I'm going to change that number to 200. Okay, so what's the prevalence going to be? I'm going to shrink these a little bit so I can squeeze more into this one page. Nope, didn't work. Try it again. Yeah, there we go. Okay, so what's the prevalence going to be? Well, the prevalence is the odds of having that condition in this population. So we know the prevalence is going to be 200 people out of 1,200 have that condition, right? Makes sense? So now that we know that, that's about 16, 17% of this population has this condition. Okay, so now let's take a look at what the specificity, we want to see how good a test this is. What's the specificity of this test? Okay, specificity of the test is how good it is at identifying people that have the condition. Well, out of the 200, if I look this in the columns, this represents all of the people that have the condition. This cell represents the ones that tested positive with the diagnostic test. This cell represents those that tested negative. So now if I look at this, I'm going to say to myself, okay, well, the probability that you were identified correctly as having the condition is 140 out of 200. So our specificity is 140 divided by 200, or 70%. The specificity of this test is 70%. 70% of the time it will correctly identify someone as having the condition. Okay, so now down here we have 60 people that were tested, that the test said were negative, but in fact they have the condition. That's a false negative. Okay, I'm gonna see if I can't. I'll do it over here. So that first cell, do it a little further out. That first cell is true positives. The cell below it is false negatives. Those are people that tested negative but actually have the disease. Okay, so let's do the same thing now for the sensitivity. Okay, and the sensitivity is a representation of how good it is at identifying people that do not have the disease. Well, 1,000 people out of the 1,200 do not have the disease. It got it right for 900, but it got it wrong for 100 of them. So how good was it at identifying people that didn't have the disease, the specificity? Well, it got it right 900 out of 1,000 times, 900 over 1,000. The specificity of this test is 90%. 90% of the time, if you don't have the disease, the diagnostic test will say you're negative and be correct. So now let's take a look at what we have here. That means that that cell down here is the true negatives, and the cell at the top are people that tested positive but don't have the disease, so they're false positives. Okay, so that's, if we look at that outline, that's what those cells represent. Okay, just so we can see that on the side there. Okay, so the next thing I might want to know is, I got 210 people in this population that tested positive. How reliable is a positive test in this population? Well, I'm going to call that the positive predictive value. How good is a positive test at determining whether or not you have the condition? Well, 210 people tested positive, only 140 of them had the actual disease. So the positive predictive value is equal to 140 out of who really are positive out of the 210 total who tested positive. So the positive predictive value is about 67%. Now, sometimes, a little less frequently, people are interested in the negative predictive value. Okay, and I'm going to put that in here, negative predictive value. Okay, and that in that situation, what we're interested in is how likely is it that if you test negative, that you are indeed. These are all the people that tested negative. 996 of them were really positive. Really should have tested positive. They were false negatives. 900 were real negatives. So we had 900 people that tested negative. Out of those 990 people, how good was it at predicting that they were negative? Well, in fact, it's equal to 900 people who actually were negative out of the 990 people the test said were negative. So its specificity is about 91. Negative predictive value, the value of a negative test, is right about 91% of the time. So that's basically what you're going to do to say with your homework problem, except you're going to be working with a slightly different population. You're going to work with a population that has 150 people out of 1,200, or a prevalence of about, I guess, about 15% or something like that. You'll figure it out, about 12% or something. You'll figure it out when you actually do it. Now, what happens if you have a population that has a relatively rare disease? You're examining a population with a relatively rare condition that you're trying to develop a diagnostic test. So I'm going to leave all the multipliers in here. So the sensitivity and specificity of this test are going to say exactly the same. Let's see what happens to the positive and negative predictive value. We're usually more interested in the negative predictive value because the positive predictive value rather. We're more interested in the positive predictive value because that's what you act on. If you have a positive test, the doctor has to determine whether you need to have a procedure, might be an invasive procedure, a dangerous procedure, whether or not you have to go for more extensive or expensive testing, and so on and so forth. Okay, so we're really interested in positive predictive value. We're also interested in negative predictive value, but positive predictive value usually have a little bit more immediacy, as you can imagine. So I'm going to say this is a slightly different population, except the prevalence of this disease is very low. There's only 20 people in this population that have this condition. See what that does. Well, the prevalence is only about 2% now, right? So the prevalence is much lower than the prevalence that we're examining in the other population. What happened to the positive predictive value? Well, instead of being 67%, the positive predictive value now is only 7%. So it dropped from 67% to 7%. So of these 210 people who tested positive, only 14 of them actually have the condition. So that makes this test a lot more problematic because it has a poor positive predictive value. Did the test change? No. The sensitivity of the test, the specificity of the test is exactly the same. The only thing that changed was the prevalence. So in a lower prevalence situation, very frequently you'll find yourself with a much lower, sometimes alarmingly lower, positive predictive value. Okay, so hopefully that helps on that. We're going to come back, we're going to revisit that because it kind of comes up again when we get into Bayes' theorem. Okay, so now let's see what the next question is. All right, now you're asked, through it. Oh, in fact, it comes up right now. Let's see, question 7. What is the positive predictive value of a test with a sensitivity of 90%, a specificity of 80%, and a population prevalence of 10%? And I think I gave you a starting point for that in Excel. Let me go back there and see if I got it. Cooties. Yeah, here we go. Okay, here is that problem. Okay, so now, did I paste in the image there? I hope I did. Okay, tell you what, I'll copy it off of here. I think I can copy it off of there. Guess not. Doesn't like me copying off there. Let me go back here and pull this off of here. Desktop. Review. Do I have it in here? Nope, not that one. Oh, there it is. Okay. Okay, good. I got it. I'm going to copy it into my little sheet here. Actually, I copy it into the spreadsheet. I think it's going to be easy to work from a spreadsheet here. Okay. Let's bring this formula in here so we can see it. Okay, and I'll blow it up a little bit. It's a little bit more obvious. Let's examine what this stuff is saying here. Okay, so Bayes' theorem, how can I describe this? Let's see, what's a good way of saying this? One of the ways that we describe Bayes, I'm gonna have to bring up this sheet so I can write. I'm gonna connect my tablet here. I think this will wind up being better. In fact, a little bit more descriptive. Okay, let's see if this starts up. Okay, turn this on. Okay, so now the way we often use Bayes' theorem is we say the probability of A given that B has occurred. These are two events. A is one event, B is another event. The probability of A given that B has occurred is equal to, let's see, probability that a probability of B, probability of A given that B has occurred times probability of B is equal to the probability of, now I'm going to have to wing it here. Let's see. The test is probability that you have disease, you're going to test positive, is probability of B given that A has occurred plus the probability of A, I believe. I think I got this right. Okay, you're going to have to trust me on this, but I think I got it right. Okay, so now one of the things you can see right away is I can take this, just divide both sides by the probability of B, and just move this over to this side. Probability of B down in the bottom here. Okay, so now I'm going to translate this into something that makes more sense in terms of diagnostics. Okay, I'm going to say that A is the probability of having the disease. Right? And I'm going to say that B is the probability of testing positive. Okay, so now we have all A's here and all B's here, so I should be able to just substitute this event. This is one event we're interested in, this is the other event we're interested in. So I'm going to take this formula that we've just kind of straightened out, just rearranged a little bit, Bayes' theorem that we rearranged, a general formula Bayes' theorem. And I'm going to say, okay, A is the probability of having the disease, and B is the probability of testing positive. So this side of the equation is really the probability of having the disease given that you've tested positive, right? B is probability of testing positive. So what is that? What's the probability of having the disease given that you test positive? That's the same thing as saying the positive predictive value. That probability is the positive predictive value. So now let's see what that's equal to. That's equal to the probability of testing positive given that you have the disease. Well, let's see, you have the disease, what's the probability in this test of testing positive? Well, that's the sensitivity. Plus, times, this is times, okay? T plus is the probability of testing positive, okay? Okay, probability that you got a positive test. Probability that you got a positive test given that you have the disease, T plus. Okay, times the probability of having the disease. What's the probability of having the disease? What's another word for the probability of having the disease? That's the prevalence. Probability of having the disease. In the first example, that was, I think, 16% or 17%. That's the prevalence. And we're going to divide that by, okay, we're going to divide that by, well, we're going to probability of B. See, well, the probability of B is the probability of testing positive. Well, you don't want to know something. There's two places where we got positive tests. We got positive tests, we got false positives, and we got true positives. So there's really two probabilities here for the total number of people that tested positive, the total probability of testing positive. And we have to determine both of them and add them together. The probability of a false positive and the probability of a true positive. I'm going to put this one first. True positive, and probability of a false positive, right? False positive. Okay. So, and we need to add those together, and those together are the percentage of people that actually tested positive. Okay. So what are we winding up with here? We're winding up with the sensitivity times the prevalence, which really is the number of people that have the disease, right, and test positive. And down on the bottom here, this is the total number of people that tested positive. That's what this denominator and numerator really wind up being. Okay, so I'm going to move this out of the way. And we can see down here, they've summarized it a little bit neater than I have, I hope. Sensitivity times the prevalence divided by sensitivity and prevalence, sort this, sensitivity and prevalence, multiplied together, which is the total number of people, going to be the total number of people that test positive. If 50% of the population have the disease and the sensitivity is 50%, 50% is 25%, so it's going to be 25% of the population that tests positive. And down at the bottom here, you have the two ways that we can get a positive test. One by people having the disease and testing positive, and the other one by having people not have the disease but get a false positive. That's what this second one is. Okay, so we're going to actually work that out now. Okay, so in order to work that out, I already know the sensitivity, I already know the specificity, it's given to me. I already know the prevalence, that's given to me. So now, since I see I'm going to need 1 minus the specificity, I might as well figure that out now. Equals 1 minus the prevalence, and this is equal to 1 minus the specificity. Okay, so that's going to make it a little easier for me to figure this out. So I'm going to try and do this all, well, actually, tell you the truth, you know what I'm going to do? I'm going to do this in two segments. I'm going to do the numerator, I'm going to do the denominator. I could do both together, but to keep it from getting confusing, I'm going to do the numerator first, then I'm going to do the denominator. So the numerator is going to be equal to the sensitivity, times the prevalence. Okay, here's our prevalence. Okay, so 0.045 is the numerator here. That's the percentage of the population that wind up testing positive. Okay, given that they have that actually have the disease. So the bottom is going to be a total number of people that test positive. And what's that equal to? That's equal to the sensitivity times the prevalence. The same thing I had here. The sensitivity times the prevalence. Okay, I'm going to put that in parentheses, and that's going to be added to 1 minus the specificity, times 1 minus the prevalence. Okay, I'm going to put that in parentheses so it doesn't combine all that stuff. It works it out individually. And I'm going to hit enter, and that's equal to 0.0325. And this is equal to, let's see, what is our positive predictive value going to be? It's going to be the numerator divided by the denominator. It's going to be equal to this divided by this. And it's going to be about 19%. Let's test that theory for a second. Okay, and the way I'm going to test it is I'm going to say, I'm going to set up a little population here. Let me see if I can't narrow these two out so we can see this a little bit better. Okay. I need a little bit more space here. I'm going to test that, see if it really worked out correctly. I sure hope it did, but I think it did. Okay, this is going to be, I'm going to lay out a fake population where we might have run this test. This is going to be my disease plus, disease minus, test plus, test minus. Okay, and I'm going to say that we have, and I'm going to highlight these so we can see the boxes in the middle. Okay, let's get this a little bit neater. Okay, so I'm going to say I got 1,000 people, right, in this population, randomly sampled 1,000 people. Well, I would expect a prevalence of 5% that the number of people that have the disease are going to be equal to 5% of 1,000. Whoops. Okay, that's 50 people. Since the test has a sensitivity of 90%, 50 out of those 50 people, I would expect 90% of them to test positive. So 45, and that would leave 5 people who test negative. Okay, since the test has a specificity of 80%, well, let's see, there's 950 people that tested negative. I'd expect it to get it right 80% of the time, 950 times 0.8. So I'm kind of constructing a population that matches that description. And this is just going to be equal to the 950 minus the 760. That's how many people test positive, even though they don't have the disease. So if I look at this, how many people have tested positive? 45 plus 190 people have tested positive, right? I'm not worried right now about how many people test negative. So 235 people total tested positive. 45 of them actually had the disease. So what would be my positive predictive value in this case? It's going to be equal to, out of 235, 45 tested positive. So 45 divided by 235. And in fact, look at that, get exactly the same number for the result. So our analysis here using Bayes' theorem worked just as it would have worked if we had the crosstabs for a random sample from the population. Okay, does that make sense? You guys okay on that? Okay, we have a few more people that have joined us. I'll make sure everybody's muted here while I'm at it. Okay, you guys comfortable with that? Did I answer a couple of questions there? Did I put you to sleep? Oh, good. Okay, I got a couple of responses there. Good. Thank you.